this last video of this lecture on the integral test, I just want to do one more challenging example from Donaldson's notes. Let's let S be the series given by a sum of k equals 1 to infinity of k times e to the negative k squared. We want to know, does S converge? Well, we want to apply the integral test. So the first thing is to define a function, f of x, so that f of k is equal to k times e to the minus k squared. So we have x, e to the minus x squared. And now we want to check that f is non-increasing on the interval from 1 to infinity. And here it's a little less clear. Like when x gets bigger, does this get bigger or smaller? But how do you check that kind of thing? Well, how do you check if a function is increasing or decreasing? Is checking with the first derivative test from Math 2a. How do you check if a function is increasing or decreasing? Is by computing its first derivative and seeing if it's positive or negative. So what is f prime of x? Well, we'll apply the product rule. We get the derivative of x times e to the minus x squared plus x times the derivative of e to the minus x squared, which is e to the minus x squared. And then we get a times minus 2x from the chain rule. We can factor this. There's a e to the minus x squared common to both terms. And then we get a 1 minus 2x squared. So if x is bigger than or equal to 1, f prime of x is less than or equal to 0. So for x in this interval from 1 to infinity, f prime of x is less than or equal to 0. So f of x is non-increasing. So this is common. If you have a series where you're going to apply the integral test, and that series is a little more complicated looking, sometimes you have to do a little bit of work to see that the function is non-increasing. But what do? You apply the first derivative test. Okay, so this function is continuous. It's a product of things that are continuous. There's nothing really to do here. And then it's clearly positive because it's x, which is positive, times e to the minus x squared, which is positive. So we're going to study this series by looking at the integral from 1 to infinity of f of x dx, which is a limit as t goes to infinity of the integral from 1 to t of x e to the minus x squared dx. And this integral is a little trickier to look at. What's difficult is this e to the minus x squared in the exponent. But we have an x dx here, which is really nice for u substitution. If you look at u equals x squared, then du is 2x dx, which is almost what we have here. We have a 1/2 du instead of a du. So we have a limit as t goes to infinity of an integral. We're going to have to adjust endpoints, but we have e to the minus u times 1/2 du. And now let's adjust the endpoints. When x is 1, u is also 1. And when x is t, u is t squared. Right? T squared. So what do we get? So we get a limit as t goes to infinity. Well, we have this 1/2, which we can pull outside. And what's an antiderivative of e to the minus u is minus e to the minus u. Now we evaluate at 1 and at t squared. So what we get is a limit as t goes to infinity of minus 1/2 e to the minus t squared minus e to the minus 1. So I'm going to factor it out like this. As t goes to infinity, e to the minus t squared goes to 0. So this minus 1 times minus e to the negative 1. These minus signs cancel out, so we get something going to 0. And what we get is 1/2 times e to the minus 1, which is 1 over e. And in particular, this converges. So what does that mean? So by the integral test, this series also converges. It doesn't tell you what it converges to, but it tells you that it converges. So this is the kind of integral test problem that you might see on a quiz or an exam, where the function giving your series is not quite so simple, but what you get is an improper integral that you still know how to do using something like U substitution.